I mean, in generally, after week 4, whatever doubts you have, maybe dynamic programming and all those things would be taken in the next session. But before that, any kind of doubts related to graphs, trees, right, heaps, anything, please tell. After that, I would go into the normal revision part. Fine. So let's see that. No doubts?
Hello, sir.
Yeah.
Sir, can you just solve week 5 practice assignment question number 3?
Week 5 practice.
Practice assignment question number 3.
Yes. Week 5 practice assignment. Question 3. Okay. So just a second. The graph shown below has 8 acres.
And after this, question number 4 as well.
Yeah, sure. Just a second. I'm sharing the screen. Yeah, PDSA mock would be released. We would release that shortly.
Hello, sir.
Yeah.
Sir, can you explain a whale tree?
Yeah, able tree. Okay, I would discuss that. So this question, right?
Yes, sir.
Okay. So what is this asking? The graph shown below has 8 edges with distinct integer weight. Fine. So whenever you see distinct integer weight, first thing that should come to your mind is there is only one minimum spanning tree. Okay. So I don't know the question now. Okay. So this is asking about minimum spanning tree names. So the red edges represent the minimum spanning tree for this graph. See, they represent the minimum spanning tree. Okay, so keep this thing in mind. This is a conceptual important concept. When there are only distinct edges, distinct weighted edges, you can have only one minimum spanning tree in the graph. Okay. Now, what minimum possible value can be assigned to x, y, and z in the graph without changing the minimum spanning tree? Okay. So see, what are the possible values that you can? First of all, this is a bit difficult to like this. So what are the minimum values that you can assign to the graph without changing the minimum spanning tree so that it remains minimum, right? So at first you see what are the edges which are currently there. 4, 6 is there, 15 is there in the minimum spanning tree, 9 is there, and 2 is there, right? So you have to put the values and see whether if I put, so let's say the first option, take the 10, 7, and 16. First check can be that is there any other minimum value within the edges which is equal to 10, 7, or 16. Check that. Okay. So if it is there, so what I mean is you check the red edges. Among the red edges, if there is a value, let's say 9 is there, na? So you see in the option whether one of the value is 9 in any of the option, right? If there is 9, then there is less probability of that option being correct, because if you put that 9 again, and 9 is also there as a part of your MST, right? So you can even put that edge in your MST. That may happen. That may not be a compulsorily happen, but it may happen. Okay. So the best way to check this is you have to put the values XYZ, put the values and find the minimum spanning tree directly for that. If you get another minimum spanning tree, you get the result. So many MCQ questions, the way to answer them is you do a bottom-up approach. So put the option into the question and then see. So just put 10, x equal to 10, y equal to 7, z equal to 16. Okay. So if I put x equal to 10, then just check that whether I apply Kruskal's algorithm and check. It would not take long. You can just do that. Simple minimum spanning tree construction. Okay. So
sir, I have to first put those weights and then I do the Kruskal's algorithm, right?
Kruskal's algorithm you apply. A little bit of windy voice is coming. I'm not able to hear you clearly. What did you ask? Can you please repeat?
Sir, what I am asking is
Yeah.
first I have to put the weight according to the options in the question, and then I will do the Kruskal's algorithm. That is
Correct.
the method, right?
Method. Correct. Yeah.
Okay.
That's the foolproof method. I mean, see, the more you practice problems, the more, what should I say, the faster you would get. The reason for that is you would be able to make some important observations in some options. Okay, I don't know whether such observation could be made in this option or not. Let me just see. So basically, that's one thing that I told, that if you get a minimum, so let's say what is the minimum value over here among all the minimum values? 2 is the minimum, right? Among, I think, 4, 6, 15, 9 and 2. So 2 is there. Now let's say in one of the option 2 was there. I mean, let's say some value x or y or whatever, something was equal to 2. One option was there. Okay, and what this question is asking you, that put the value of xyz such that the MST does not changes, right? So that I mean, by introducing these values of x, y, z, you do not change the minimum spanning tree. So you want to keep the minimum spanning tree same. If you put the minimum possible edge weight which is there in the MST as one of the value of xyz, then you have a huge chance of changing the MST, because that is itself the minimum tree, and when you reapply Kruskal, then it may pick x equal to 2. Assume x was 2 in one of the options. Okay, so whenever you see one of the option among this xyz, in one of them x equal to the minimum edge weight is there. Minimum edge weight means the minimum among the MST. So here 2 is the MST, right? 2 is the minimum among the MST. If one option would have been there, you simply do not need to check that. It may change it. Fine. Unless and until there is a cyclic thing coming up, it would change the MST. Fine. So those kind of quick judgment you can make to answer fast, but obviously the only proper way to answer this is you have to put the values and check whether it is changing the MST or not. Fine.
And if there is a value less than 2, that I will not check also, right? Because if less than 2 means in the minimum spanning tree, I could have taken
Exactly.
this.
Exactly.
Okay.
So these are just observation kind of. I mean, it makes your process faster, but the foolproof method is you have to apply the Kruskal algorithm on each option.
Okay, sir.
Yeah. Okay, so fourth question, right? This question, I think.
Fourth, sir. Yes, this one.
Yeah. So this is Dijkstra, right?
Yes, sir.
Let me just. Okay, so is there any specific doubt or the general how it's working?
No, I tried to follow the algorithm, and in line number 80, I mean, the condition is if
This one?
if this in line number 17, the condition if distance next v plus a weighted distance is less than the distance v, then we are updating the parent v dictionary.
Correct.
But if in case of equal to, we will not update the parent v dictionary.
Yeah, if W mat less than
Then
this.
in that case, why SDT, the option B is incorrect? Could you please check?
SDT, right? So, okay, let me just, we have to go through it. Just a second then. 3 SDT, right? SD and then T. Okay. Okay. So, I pick here 3, 4, 7. Okay.
In the first iteration, the
First
parent of
iteration, it would
A,
be
B, and D all will be S.
S, correct. Second iteration, B would be picked because 3, 4, and 7 is there. So the minimum value is 3. So B would be picked, correct? So once B is fixed, it would be 3 plus 4, 7. So I would not change the parent of D now, according to the
Correct.
condition, right? I would
Yes.
not change the parent of D. Fine. So next step, what would we pick? D is done now. 4 is there, 7 is there. So I would pick 4. That is, I would pick A. So once I pick A, what would happen after that? I would relax this edge. So it would become 4 plus 1, 5. So C became 5 now. Okay. So now I have 5 and 7 in my heap or whatever in your structure, 5 and 7. So I again pick 5, and again it became 5 plus 2, 7, but I would not change because again S is, I mean, it's same. So I'm only checking for lesser value. So parent of D is still S. Okay. After that, from C, I have to relax the other edge, which is 1 over here. So C was how much? 4 plus 1, 5 plus 1, 6. So E had become 6 now. Okay. And okay, so E is now 6. So what are the elements now there? 6 is there for E and 7 is there for D. Minimum is again E. So I would pick E again. Okay. So then after that, 6 plus 2 is 8 and 6 plus 4 is 10 towards D. Okay, great. So 8, 10 and 7. So now I would pick D, right? So 7 plus 3 is again 10, and it was already 10 from E. Remember, it was already 10 from E, right? So that's why I would not change the parent of T now, because D is coming later, right? E was already the parent of T, because T was also getting 10 when I come from E. So if I see that, let me just see. So I picked up C, correct? So C was 4 plus 1, 5. So C became 5. After that, I picked C. 5 plus 1 was 6, right? So E was 6. So 6 plus 4 was 10. So T's parent was E and the value was 10. D was initially 7. And when I picked D, 7 plus 3 again became 10. Correct?
Got it, sir. Thank you. Thank you.
Huh. So it is SSET. Okay, anyone else? Any doubt in Dijkstra, since we are already on one example? Okay, fine. Any question, practice question, any other question?
Can we try solving one PPA2 of week 5, or that will be for later?
Programming assignment. Okay, so we would do that at last. Let us then
Okay.
finish the revision then. Okay, so if no specific doubts as such, let me ask a few questions, that then we would go into the discussion part. Fine. So let's say a question is asking you, that in a heap, n elements are there. Okay, n elements are there already, and it's a heap. Let's say it's a min heap. It's a min heap. Now the question asks you that if you have to insert n by 4 elements, new elements to be inserted, number of new elements to be inserted is equal to, okay, so if someone of you are not is not aware of this thing, so we generally use this pound symbol to denote number of, okay, shortcut, I mean, it's a local way of writing the pound symbol, the number of new elements to be inserted. Okay, so I give you that you have to insert n by 4 new elements into the heap. Okay, or for that sense, to generalize it, let's say I can also give n by 2, I can also give n. So basically, if I generalize this thing, the question is the new number of new element to be inserted is actually something around order of n. Okay, so if this is the thing, a heap is there with n elements. You have to insert order of n new elements into the heap. How much time would this process take? So that's the question. Okay, so this is a theoretical question, as you can see. Okay, just tell me how much time would this process take. So how much time would inserting a single element into heap take?
Login.
Correct, log n time, right? Single element insertion, log n time. Yeah,
Won't it be n log n because we're inserting n by 4 elements?
correct. So if if we are inserting n by 4, or I mean order of n elements, so it would take n log n time. But there is a catch over here. Okay, so just keep this thing in mind. And as of now, we would also discuss it briefly, but may not be, I mean, if you are not, if you do not get this in depth, that's okay. We can again discuss it on discourse, but just keep this thing in mind as of now. So if there is already a heap whose size is, let's say, given n, and you have to insert order of n elements into the heap, it may be n by 4, n by 2, anything, order of n. Okay, so it's better to actually not call the insert function of heap on all those n elements, or n by 4 order of n elements, because you would get a complexity of n log n time to do that. But let me ask you once again, what was the time required to create a heap? You all remember? What was the time required to create a heap? I mean, no elements are there, just an array is given to you. We have learned, right, how to create a heap from an array just by calling the heapify function. So let's
Sir,
say
n log n.
creating heap n log n.
Sir, n heapify operations.
Order of n.
Order of n. Actually, I mean that's why I was asking. Creating a heap from a totally random array, creating a heap from a random data set array would take you order of n time. Now why order of n time? So let me answer this question first. If creating a heap from a random data set of size n, or an array of size n, right, that takes the order of n time. Now if this is a fact, if this is given, then, and again you want to insert order of n elements into a heap, right? Now, I mean, let's come back to this question, considering you know this fact. So it's not intelligent to actually call the insert function on this order of n elements. Rather, what you can do is you can assume that I do not have any heap at all, right? If you call insert function, it would take order of n log n time. But if I say you to build a heap from n elements, it takes order of n time. Okay, so you can assume that I do not have any heap at all. In a heap, there are n elements, right? So you just assume that I do not have any heap at all. So whatever data I have, which is actually a heap given to me according to the question, I would assume it is not a heap, right? So there are total n elements, which was a heap, this part. And then I would add n by 4 elements more. Just extend the to list, right? In case of Python, you can just extend it. Or let's say I'm just saying that you're concatenating it. So n by 4 elements, fine. And simply what you would do after that, you could create the heap from this whole element together. You just assume that I do not have any heap. So you are not inserting, you are creating from the very scratch, just by increasing your data set from n to n plus n by 4. Okay, then you call the create heap, or which we
Sorry, sir. What do we extend the data set to from n to n plus?
Just the new elements, the n by 4.
Acha, okay, got it, sir.
Right, you just increase the data set and then you just call the whole thing on create heap. So what would happen essentially is, if I tell you that in order to create a heap of n elements, it takes order of n time from a random data set. So how much time it would take? Order of n plus n by 4, because that's what your data set is. So it's essentially order of n. But if you would have done the insertion, considering this part to be a heap already there, right? And this new part, this part n by 4 part, which is which would be newly inserted on this each n by 4 element, if you would have called the insert function of heap, so as someone rightly said, it would take n log n time. Now the main doubt is this fact that creating a heap from n elements would take order of n time, because again, as one of you said, I mean briefly, that you have to do n heapify operation, correct? So why it would take order of n time? You are correct. You have to do n, maybe not n, but order of n. Why I am not saying n? Because let's say if this is a heap, I mean not a heap. Let's assume this is not a heap, but I'm just drawing the physical structure of it. Okay. So let's suppose this is a mostly complete binary tree, and you want to make this into a heap. Okay. You want to make this. So let's say this. Okay. So let's say this is a mostly complete binary tree, and you want to make this into a heap. So you would call Heapify on which nodes? Would you call Heapify on this node, on this node, on this node, on this node, on this node? No, because those are your leaf nodes. You do not call Heapify on leaf nodes. That's not required. So if you remember, we used to call Heapify from the parent nodes, first parent node from the bottom. That's why we had those n by 2, right? That you start the for loop of calling Heapify in case of building a heap from n by 2. So let's go to the summary page. Heap was in week 5, week 6, I think. Okay, just a second. Build heap. See this part for k. You, what is this n? You see from n you are starting till it goes to -1, but that is basically you reach the end. From n you are starting to call the build heap function. I mean heapify function, max heapify, right? So what is this n? See over here. It's self dot a, that is that your size, self dot a size, length of self dot a by 2, -1, that is for adjusting the index value. So you remember we did this thing. So what does this thing mean? So in a mostly complete binary tree, we discussed this, that 50% of the nodes would be leaf nodes and 50% of the nodes would be parent node. So in order to get the first parent node, first means from the bottom of the tree, the first parent node that you would get, in order to get the index of that, right? Since I know 50% of them are leaf node, I can just say that, okay, so n by 2 are leaf, n by 2 are parent node. So the ending part of the first n by 2 is the index of my parent node, first parent node, right? So if I put the numbers over here, you would see this. So how many nodes are over here? How many nodes do I have? 3, 4. These are indices 5, 6, 7, 8, 9, right? I have 9 nodes, and that is basically I have 10 nodes. Sorry, I have 10 nodes. So if I do this 10 minus 1 by 2, which is essentially 4, integer division, right? Integer division I am doing. So if you get that, so you would see this thing, that 4 is the index of the first parent node from the bottom. Okay, 5 is not a parent node, 6 is not a parent node, 4 is the parent. The reason for that is, since heap is a mostly complete binary tree, half of the nodes would be leaf nodes. So the other half, this half, that's why this half factor is coming. The other half are parent node. So you go over here, and then you start calling Heapify, which is what you are doing over here essentially, right? Self.max Heapify, you are calling it from n. N is equal to this expression, right? N minus 1 by 2. Fine. So okay, fine. So n by 2 nodes are leaf, and I am not calling Heapify on n by 2. So that's okay. But still I am calling Heapify. Still I am calling Heapify on how many? N by 2 nodes, n by 2 parent nodes. Now we know that Heapify takes log n time. So this should be again n log n. Anyways, I did not gain anything. Even if I would have called on all the nodes, trivially it would have been n log n anyways. So dividing by this half factor is not giving me anything else. I am still getting n log n time. But why I am saying that it's not actually n log n, it's order of it. So that analysis is what we call the amortized analysis, as we have come through that in many parts of our discussion while analyzing algorithms. So amortized analysis says you that maybe one of the iteration takes some more time, but maybe the next iteration takes lesser time because of that. Like in union find we discussed, we would discuss again, but just like we discussed. So the overall average time of each operation is much less. Okay, you should not think about that it's log n every day. So what happens particularly while building heap? Okay, Heapify takes log n every time. Do not confuse it. Just keep it in your mind that Heapify would take log n time, but only while only while constructing the heap from scratch, this particular behavior is observed, and that's why we say that if you have to insert around order of n elements into the heap, it's better to build the heap from scratch. What is that observation that we see while creating the heap? In general, I'm repeating again, in general, Heapify would always take log n time, because basically you would have to come till the leaf level while working on Heapify. The recursive Heapify calls would go to the leaf level. But what happens when we first time create the heap? See, when we first time create the heap, let's come back to this example itself. Okay, what's happening? So I would start calling from 4, right? Heapify would be started calling from the 4th node. Now we say that Heapify takes log n time, correct? But what is log n over here? In this case, how many nodes do I have? I have 10 nodes. So log n is basically log 10. My base is 2. So it would be 4, right? I mean 3. Sorry. So it would be 3. So Heapify should be called on 4 at least 3 times. Not at least, at most 3 times. So you see, but we are not calling Heapify around 3 times on 4. Because why? Because I have only one level below 4. Heapify would not be called recursively. Okay, so you are calling. Sorry, can someone is unmuted? Can you mute? Yeah. So basically you are calling Heapify only once because this level is only one level. Same would happen for the 3rd node as well. You would call Heapify only once because this is just the penultimate level of the leaf, just above the leaf. Same thing would again happen for 2. You would not call 3 times. Now assume only at this level, basically you might need to call for 3 times. Okay, so the worst case of log n, that is fine. If you do a random Heapify to in a already given heap, just a random Heapify to a random node you do, sorry, I mean a random node you call Heapify on. So that would take order log n time, and that is a good estimate for that because you don't know where that node would end up. But when you are constructing the tree from bottom to top, right, you are calling Heapify on each node, assuming that every time it would take log n time is not a very good analysis. You can actually bound that a little bit more. And that reason is you are not actually getting into log n time recursive call when you are towards the bottom part of the tree. So this is a small example. Just assume there are 2000 nodes in your tree and you are assuming, and what would happen just above the leaf level. So let's say 2000, this is the leaf level of the 2000 node tree, correct? And we know that 50% of the nodes are leaf nodes. So around 1000 nodes are consumed over here. So you know that since this is a heap, so all of these two would be mapped to a single node like this, right? Something like this. So this level would have something around half of the leaves, half of the nodes, correct? So this level has a huge number of nodes, what I mean, right? Just the penultimate level. But in this huge number of nodes, you are only calling Heapify algorithm once because it is just above the leaf level. So the successive recursive calls of Heapify would not occur because you are at the just the level above the leaf level. Same thing would happen even for the top. You are not calling Heapify till log n times every level, right? At the worst case, you are calling. So that's why when we are building the heap from bottom to top, I would say it's a very loose or conservative estimate to just think that log n would be taken every time. It's not like that. When you are doing a random Heapify, that's log n is good to assume because you don't know. But when you are constructing from bottom to top, you can actually be a bit more analytical and say that, okay, no, it's not log n every time. Now, what it is actually, that derives the order of n complexity, but that we are not going into that discussion because it's easy, but it's a little bit it is proven a little bit differently, and that is not required. We would discuss that later. We would surely discuss that, how that proof is coming. If you are interested, you can check the Corman book, but I am not going into that intentionally now. Okay, so it's basically a small integration of a fact and summation of a fact, you can say, and basically you just have this number of times you are calling Heapify as a function of the height of each node, and then you create an expression. So basically, if I assume that each height is denoted with a value, say let's say h. Okay, so how many nodes are there in at a particular height that you find? And I would say that your Heapify would actually take around log h time around for each of the nodes at that level, and then you do a summation of h equal to basically 1 to log n. Okay, so not necessary. We would not go into that discussion now. We would discuss that later. But just have this intuitive idea, that's important, that if you are going from bottom to top, you are not exactly calling Heapify log n times each and every time. So a bit more analytical way, we can say that it's not log n every time, it's lesser than that. Okay, so that boils down to the expression of that just if you quantify this thing in an expression and solve it, you would get order of n complexity. Okay, so as of now, what's important is keep this thing in mind. If a heap is already given whose size is, let's say, order of n, and you have to insert order of n elements, n by 2, n by 4, n by 20, n by 36, whatever order of n elements you have to insert into the heap, it's better, or maybe more than order of n in square element. Okay, so it is always better to actually assume that you do not have any heap and you create the heap from scratch. Do not go for inserting the n elements into the heap. Okay, so the answer to this question is order of n. Okay, not order of n log n. Okay, fine. The proof of this, if you want, we can discuss on discourse. You can check the CLRS book if any one of you are interested, and we would also explain in one of the sessions after the completion of this quiz. Fine, just keep this fact in mind. So that was one thing. Any doubt in the intuition? I'm not going into the analysis that much. Any doubt in the intuition you want to ask about?
Instead of n by 4, if suppose finite number of elements are to be inserted. Say suppose
Then
instead
go
of
for
n by
insertion.
4, suppose 20 elements are to be inserted.
Yeah, go for insertion, because until and unless it is in the order of n, right? So I say you, I mean, you do an insertion for 20 elements, right? So how much time it would take? 20 log n, correct? And if you create the heap from scratch, then n elements were already there. You add 20 elements. So what would it be? It would be order of n plus 20, which is order of n again, but this is order of log n, because constant factor doesn't matter in either case. Okay, so unless and until it is in the order of n itself, okay, you better go for insertion. But as soon as this factor goes in the order of n, so this would become order of nc, because this is multiplication, but this is addition. So even if I do n plus n, it is order of n only. Getting the idea? So that's why it's important that unless and until it is said that the insertion number of elements to be inserted is also in the magnitude of n, you go for insertion. Is it okay?
And suppose instead of order of n, if it is something like order m elements, something other than n,
M
which is
elements is
not
again,
constant.
see m. So see, whenever we are dealing with an algorithm, you have to mention all the variables in the question. So unless and until a variable is mentioned, I would assume that it's a constant. So if there is no mention about a value of m, or it does not represent something significant in the algorithm, and if I just say that a heap is there whose size is n and m elements have to be inserted, we treat m as constant in algorithm. In mathematics, we would treat m as a variable, but here it's a constant because it has no significance with respect to the working of the algorithm itself. So you again go for insertion. It's m log n.
Thank you, sir.
Sure. Okay, so keep this fact in mind. You can read it out again or ask any doubt if you are interested in it, but keep this fact in mind. Okay, so that was regarding Dijkstra, sorry, Heap. AVL tree. So AVL tree, we have discussed that in AVL tree session, but I would mention one very important thing, a generalized view of AVL tree once. So let us see, I mean, from the theoretical perspective only I would state, then we would go for the revision part. See, in case of AVL tree, let us discuss that. Let us do a generalized way. Say, let's say like this. Okay, so let me just set there. So this node is the new node which is inserted now. Okay, and fine, I'm just randomly drawing a structure of a tree and assume that this particular, here we have an imbalance. Okay, this T1, T2, T3, these sizes are such that the sizes of this subtree. So these T1, T2, T3 are basically subtrees. Okay, and this is the new node, and I have an imbalance over here. You find the imbalance from the new node which is inserted. You check each node in the path to the top. Wherever first time you would get 2. Okay, first time you may get 2 anywhere in between. So the first node where you get 2, that is the node where the first imbalance is occurring. So consider that node and then you apply your rotation. Okay, so what we would do first time, we see the new node is there and the first unbalanced node I have got over here. This is the first unbalanced node. So you check in which direction from the first unbalanced node, that you got while moving from bottom to top, right? The first unbalanced node that you got, from there in which direction I have to move in order to reach the newly inserted node which created the unbalance. Okay, so if I see in this tree, I have from the from the unbalanced node, I have to first go left and then again I have to go left. Okay, I may not reach this node, but in order to reach this node, I have to take this path, one left and then again another left. Okay, so this marks your LL rotation. This means that you have to apply LL rotation. Okay, same thing, just have any random tree. Okay, I'm just drawing randomly. I'm not worrying about the balance. Just keep that thing in mind. So let's say here you have one subtree T1. Here you have one subtree T2. And here you have done an insertion of node. Similarly, let's say here again we have some nodes. Okay, but we are not assuming anything about them. Some T4, anything. Yes. But here, this is the node where you are first getting the unbalancedness. Okay, you go from, so this is the new node, right? You go from here to the top and check each balance factor of each of the node in this path. Okay, in this path you check the balance factor of each of the node. So this is the first node where I am getting an unbalance, which is, let's say, 2. Okay, so actually it should be -2 in that case. Yeah, so I'm getting an unbalance of -2. Okay, so again check which direction I have to go to reach the new node from the first node where unbalance is occurring. I see that it's right side I have to go, then again I have to go right side. Okay, so you see that this is an RR rotation. So RR rotation means what? It's a R, it's towards right. That means you have to undo it by rotating it towards left. Okay, rotation is RR. That is, we have to rotate it towards left. Okay, you see that's skewed towards the right. And similarly, this tree, so this is an LL rotation. We have to rotate it towards the right. Okay, here it was towards the left. Here it is towards the right. So this is one thing. So similarly for LR and RR also, sorry, LR and RL, whatever it is, you can see that if the structure would be something like this. Okay, let's say this is your new node. And let's say here again we have some other trees and all, T3 or whatever. But let's say I get the imbalance first time over this node over here. Let's say I get -2, suppose. Okay, again apply the same logic. Where is the first unbalanced node? Here is the first unbalanced node. Where is the new node? Here is the new. So which direction I have to travel? First right and then left. Right, let's say suppose here another node was there. Okay, so first I have to travel right, then I have to travel left. So this is R and this is L. So there's an RL rotation. Now once you get into an RL rotation or LR rotation, RR and LL is very simple. In case of RR rotation or LL rotation, right, when you get such, only one rotation is needed. Only one rotation. Okay, I would take example briefly. For all the rotations, I would take one example and yeah, then we would conclude this ABL tree. So only one rotation is required. But for LR or RL rotation, you need two rotations. You need two rotations. Right? So here you get an R and L. So this is how to spot whether it is LR, RR, whatever it is, LR or RL. Fine. Now how to do the rotation. So if I let's take an example.
Excuse me, sir.
Yeah.
So how will we identify again the number of rotations to be done?
Number of rotation, yeah. So number of rotation means, so you don't have to check the number of rotation. You only have to check whether it is LL, LR, RL or RR. Yeah, RL or RR, how would you check? That's what I said. No? So let's say this is the new node. Consider this tree. This is the new node that you have added. Okay, in this tree. And the first, go from bottom to top. Apply this logic, you would not never be wrong. If you go from the new node, the node that you have inserted, from there check its parent, then again check that parent of parent of parent, like that you go up to the chain. The first time where you get an imbalance, I am assuming you are getting an imbalance over here. These trees are not balanced or anything. I'm just taking an example. Okay, so let's say the first node in the chain of moving up to the parents from the newly inserted node, from this newly inserted node, you move from parent to parent. And this is the first node where you get the imbalance, let's say -2. Okay, you get a negative -2 imbalance. So is the first -2. As you, if I get a -2 over here, then this is the node that I have to consider. The first -2 or 2 in case of our LL. So wherever you get, consider that. So this is the first node. Now you check in which direction I have to move in order to reach the newly inserted node from this node, the first imbalance node. Okay. So which direction in this particular example, in which direction I have to move? You see that I do a right move and then again a right move. Only two things I have to consider. 2 times, first, second, that's it. Okay, I do not have to reach the new node like that. I have to just think about the direction. So let's say if there, like this, another vertex was there. Now the question is in which direction you have to move. This is the -2. You see, I move first right in order to reach the new node. And then again, I would not move left because the new node is over here. So again, I have to move right. So this marks your RR rotation.
Got it, sir. Thank you.
Like this, you apply same logic for LL, LR, RL, RR, anything. Okay, so this example, this is -2. This is the new node that I have inserted. Go from the first imbalance node towards the newly inserted node. At first, I have to move right and then not right. I would not move here because this is something else. My new node is over here. In order to reach here, the path is towards left. So you make a right, then make a left. So this is an RL rotation. Now, once you get this LR or RL, you know that it's LR or RL is always a 2 rotation remedy to balance, and RR and LL rotations are always a single rotation remedy. So now let's.
Hello, sir. How
Yeah.
how it is -2?
Which one?
The upper one. Yeah, this one RL. I think it should be -1, na?
No. I'm just taking an example. This is a T2, right?
Yes.
This is
Okay.
a T2. I have not taken any assumption about the height of it. I just wanted to discuss how you can locate whether it is LLRR, and the fundamental difference between locating it. Okay, now I would take an example which is proper. That's what I said, that it's not about the height. I'm just discussing how to spot which kind of rotation you need to do. Okay, so LL or any that LL or RR rotation are quite easy to do. You know that, I mean. So okay, suppose this is kind of a tree, and this is the new node. E is the new node which I've just inserted. Okay, so if I move from here to the top, yeah, if I move from here, this is the new node. If I just ignore this E at first, do I have an imbalance in this tree? I have no imbalance, right? Yeah, I have no imbalance. Fine. So you see the degree of this is 0, degree of this is 1, degree of this is 0, degree of this is 1 again, and degree of this is 0. Fine. So if I add another node over here on the right side, then the degree of this node, if I move from, what did we say, that we move from bottom to top. So you move from here, the degree it is 0. Here its degree is 1 now. Right. And this degree has now scaled to 2. Correct. So the first time that I'm getting that unbalanced 2 or -2, from that node I would apply my IDA. So where would I have to move in order to get the new node? Left, again left.
LL.
So yeah, so it's an LL direction, moving from left and left. 2 lefts we have to make from the unbalanced node. So that is an LL rotation. And you have to move LL means you have to move towards right in order to do the balance. Fine. So what we would do, just move this thing towards right. So move the whole thing towards right. If you go, let's say B goes at the top, A is over here, then C is over here, F was lesser than C, so F goes over here. Okay. And here I have D, and here I have this new node. What was its name? A, B, C, D, E, right? E node. And B, A, C, F. From here I have D, and from D I have the new node.
Sir, do we need to shift A, or do we need to replace B with D and keep B on the right side of D?
Yeah. So if you move from D, right? So you have to push A below and keep A as the left. Keep B as the left child of A. That you can do. Or if it is like this, so let's say if this is a left child, A is here, then B is here, C is here, F is over here, and B like this here moving to D, right? Is there any imbalance over here? 1 minus 0? No. B is the left child is D, and E, right? 2, 2. This again 1, this 0. Fine. So I inserted D after that. D is 0, here it is 1, here it is 2 minus 0, which is 2. Correct. And here again I would win problem. So at first my LL rotation is coming over here. Okay. So this is one step, so you can replace it with A, right? You move here D, you move here B, you move here E. So this is your first step. Okay, so this is one form of rotating LL. Another form of rotating LL, sorry, this thing is wrong. Just a second. Yeah, just got confused while drawing this. Okay, so you rotate this thing, LL rotation towards right. Okay, so you rotate this pivot element, which is D over here, and move B. If I move it towards right side, right, so B would come down, D would come at this point, and E would be the left side. Okay, and then I get a balance factor.
So how I remember is like B is the point of imbalance. So we
Correct,
make
correct.
B as a pivot, and then around that we are rotating everything.
Not B as the pivot. Your pivot is, I mean, yeah, I mean, you are basically moving D up. I mean, whatever
Yes.
terminology.
So yeah. So keeping B as a kind of peg, we are pulling everything from below,
Correct,
and
correct, correct.
then D gets shifted and B gets shifted towards the right of the pivot.
Yeah, yeah, yeah. Shifting is fine. Mainly thing is that
Because
when you are,
B has always towards the left of the A.
yeah, that is the greater, I mean, greater than lesser than factor. Yeah, that would anyway would be handled implicitly if you rotate it correctly, right? So here the rotation was wrong because I considered this thing. I mean, I just got confused over this pivot, and yeah, so that's why it was like that. So you get the LL rotation like this. So you consider this as the pivot. I mean, whatever you say. I mean, you this would move up. Your D would move up. You are moving towards right, right? So B would come down. Another thing, if you do a rotation even considering D as the pivot, then again you have to check for LL-ness. I mean, otherwise it would be wrong. Fine. So anyways, so that was LL rotation. If you consider this similarly like RR rotation, a let's say this is also 0, this is 0, this is 1 minus 2, which is minus 1, right? This is 0. After that, I insert an element over here. Let's say F. So this is 0.
C is not 0, right? C is
minus 1. Yeah, no, I'm modifying it. So the new element is F, right? Before that, I just check whether the balances are okay or not.
Okay.
So C is 1 minus 2 is minus 1. 0 minus 1, 1 minus 2 is minus 1 again. And here it is 1 minus 3, which is minus 2. B is 0, B is 0. Fine. So again, you check that thing. The new node is F, right? The last node which I added. So I move towards right in order to reach F. Then again, I move towards right in order to reach F. Two right rotation I made. Fine. So this is RR. So I would move towards left in order to make a balanced tree. And RR and LL is just a single rotation. After that, we would go for LR and RL. Right. So let's say 2 is my unbalanced node, which I have to change. So what I would do is I would consider the C, right? The next node I would consider as the pivot, and I would rotate it towards the left side. Fine. So C comes here, A comes below, B comes below than that, and you see that C's left child was D, correct? And when I moved C to the top, then I have to place D somewhere, correct? Now D, what is the value of D? Correct. Yeah. So A is lesser than D.
Right side of the A.
Correct. And C is greater than. So D is lying between A and C. If I have the position of A and C like this, where can I put D so that it remains in the middle of A and C? I can put as a right.
Right of A.
Right.
So now just put everything else as it is. Okay. So that is your simple LL and RR rotation. Now for LR and RL rotation, let me just generalize it rather than taking a simple example. So let's say we have a node A. I have to think a little bit about it. A, B. And then let's say we have a subtree T1. Okay, I have another subtree over here. Okay, let's LR, right? LR. Okay, anyways, so I can add it anywhere. So let's say I can have the node over here also, or I can have the node over here also. Doesn't make any difference, but let's take any one of the examples. So let's take it over here. So this is the new node. And let's say I have to adjust the height. So let T1 be of height h. Okay. And let both of them be height h minus 1. Okay. And let T4 be of height h. Okay. So if we have that, so basically this node's height is h. This node is at height h. Fine. So what would be the index, sorry, balance factor of C? It would be h, that is the left subtree left side. This is the new node. So left subtree maximum height is h, and right subtree maximum height is h minus 1. So I would have a difference of minus 1, right? C's balance factor would be 1. And if I see for B, what would be the balance factor? Left subtree is height h, and right side I have the maximum height of h plus 1. Yeah, so because h minus 1 is here up to this level, right, and h is over here, so I have a total negative weight because h minus 1 was initially not, sorry, h height, this new node was initially not there. So I have one more length over here. So left minus right subtree would give me one extra length. Right subtree is one more, this edge corresponding to one more, and that's why it's minus 1. Okay. And over here it is height h. So yeah, now it is minus
So
1.
leaf node height will be 0, no?
Which one?
The new node, which is leaf node, you're inserting. The last node, new node.
For which node? B.
No, below T2, we are inserting new node. So that will be of height 0.
Oh, no, this is 0. I am just telling that the height is h, the total height over here. I am just considering the lowest level as height h. This is height, not balance factor. Balance factor is 0 only. Height.
Okay.
This height. Height is h. Total height is h. That's what I'm saying.
Okay, since the root node. Okay.
Yeah. Balance factor is 0. Okay, so basically what I want to discuss is, so let's say this is a general tree. If I delete all this now, you see that this is a general, in any kind of LR rotation, you would get a tree like this, because I mean, just a general way. So why? Because if I see this is the new node, and here is the balance factor you are getting first time. So L is the first, this is the first direction that I have to take in order to reach B, and this is the second direction, LR. Right, because the new node is over here. Notice that even if I had the new node over here, that's what I said, even if I had it over here, then also it would have been LR, L and R, because in order to reach any one of these T2 or T3 tree, I have to take the left and then the right. Okay, so in either case it would be LR. So let's take the first example. So now I have this structure and I have an imbalance at A and I have to balance it. So how we will do that? So see, first L and R is there. So at first, whenever you see LR or RL rotation, there are two rotations that we have to make. First, we would start from the bottom one. So first R is there, which is a right rotation is there. So we have to rotate towards left side in order to have it, right? We have to rotate it towards left side. So first just rotate it towards left side, left rotation, left side rotation. What would happen? I would rotate, C would come over here. So let's say A is already there, right? So left side rotating, C comes over here,
B,
B comes at the bottom,
T4,
T4 tree, this is a subtree.
T2, T3.
Okay, yeah. So C, and here I have T3. What about T2?
After B.
Correct. Same observation again. We would make that T2 is lesser than C but greater than B, according to the first tree. Lesser than C but greater than B. So that's why this is the appropriate position. T2, and the new node was, it would be just the way it was initially, like this. Okay, and T1. So this is only the first time I am rotating, right? Only the first R rotation, the rotation corresponding to R is done, but still this L was left, right? So that I would do again another rotation. So this is rotation corresponding to R, which is basically a left side rotation. And now I would do rotation corresponding to L, which is a right side rotation. Okay. Now the imbalance was over here, so C would come at the top, correct? So I would bring C to the top.
B,
Right? B remains over here, T4 remains over here. Now we have to think where we would place each one of them. So T3 is greater than C and lesser than A, correct? So
T3,
T2 is greater than B and lesser than C. So T2 is not changed, T2 would remain as it is. So you finally get this balanced. Now this is a balanced. So the theoretically, while solving rotations, okay, the process that you have to follow is put the new node, go to the from top to bottom, move like this, get the node where you're first observing -2 or +2 factor. Considering that node over here A, take the path, you know, in the way, I mean, to reach the new node. So you see that here left and right is there. That's what I was saying. Even if this new node would have been inserted over here or here or here, anything doesn't matter, right? Even if it was inserted in the T3 subtree, still we have to take left right rotation. So the process would have been similar, just the thing that T3 would have this new. Okay. So you take that path, now you know LR rotation, right? Now since this is R rotation, so you first start from the beginning, do not start from the top, because at first you have to move from bottom to top. Just sort out the subtree, then you move to the main tree. So you pivot this C, move it to the top, and then you process. Okay. I mean, depending upon your terminology, you can say B to be a pivot or C to be a pivot. Basically, you have to move the node which is below the imbalance node to over here. And then again, you have to apply the right side rotation, which is the L rotation. Okay. So yeah, check this out. So that is, this is what LR, right? RL would be just similar, just this mirror image of that. Okay. I'm not discussing that again. Just the same thing would happen. Just the mirror image of this. Okay. Anyways, ABL tree would again be discussed tomorrow. In general, if you have any doubt, you can ask in the ABL tree. Otherwise, I will go to the normal revision.
It takes a little time in doing all these rotations.
Yeah, correct. And still, I mean, you have to be careful while doing that. The best thing is you check the factor. I mean, sorry, not the factor. You check the sorted order. If at the end, after making the rotation, if the sorted order does not make sense, it's not a binary search tree, then you must have done something wrong somewhere. Then it's fine. Then you can just do that. So you have a check. At least you know that you did wrong, and you can again retry. Fine. So that's ABL tree. The coding part of ABL tree. So this thing we discussed now, that you get the first unbalanced node, move towards the new node, and then you would get whether it is LR or RL. That same thing we are doing in theory by applying this method. But what you can actually do in code is you check whether the newly added node, how can we check? So let's take this example only since we are discussing. Since let's say this newly added node, okay, sorry, not this one, right? Yeah. So this is the newly added node. So how to check whether it is L or L is fine. L you can check by simply checking the balance factor. If the balance factor is positive 2, then you know the left subtree is, left subtree is more in weight, right? So the left side has more elements. So that means your left side is skewed. Otherwise, plus factor would not have come because you are subtracting left minus right while calculating balance factor. So it's plus 2 means the left side has more elements, and that means you have to rotate towards right. And that means left side has more elements means it's essentially L rotation. So that thing is fine. First thing you can figure out. But in code, how can you check this thing? That the next part, whether it is LR or LL, that you don't know. So you can simply check that by checking the newly inserted value and the value of this node, right? Just the node below the unbalanced node. How can you check? Because see, if I am putting a new node value which is greater than B, then it would be obviously in the right subtree of B. And if I am putting a node which is lesser than B, then it would be on the left subtree of B. If I am putting a node which is lesser than B and it is in the left subtree, it is over here, then obviously it's an LL rotation. And in the current example that we have now, if I remove this.
So B will be negative in LR and positive in LL.
B would be negative in LR and positive would be in LL. Yeah. But yeah. So you can check in either of the way. There are multiple ways of checking this. Okay. I prefer this greater than lesser than check. You can do that. Fine. So ABL tree is done.
Now, could you please repeat like how it will be LL or LR?
From the coding perspective or from the?
Yeah, in the code you said no, how to check whether it will be LL or LR.
LL and LR is, that's what I'm saying. So let's take this tree only that we were discussing, this tree only. Okay, so assume this is the new node which I have inserted. Fine. And I need to check whether it is an LL and LR. So at first you calculate the balance factor of each node in code. That is the first step. So the balance factor, you get the balance factor. A is the first node where you are getting a 2 balance factor, and that is a positive 2, plus 2. Okay. So once you get a plus 2 balance factor, what does that mean? How are you calculating balance factor? Left tree minus right tree, correct?
Yes.
So if you get a positive value of this, if you get a positive, that means left tree has more element. It's deeper. It's more deeper. So that means you have inserted towards the left, sorry, in the
Yes, left tree is skewed.
Skewed, correct. So the first thing that you can assume is the corresponding to A, the left side is skewed. So that means obviously I have to apply a left rotation. So the first L is there. First L I could actually figure out. Because left side is skewed, so I would apply a L rotation. So I know that left subtree of A has to be considered. So that is step 1. Now I have to figure out LL or LR. So for that, what I have to judge is corresponding to what are the two options. Either it can be LL. So basically I'm talking about this part LL. That is the left subtree of B, or LR. That is the right subtree of B. Okay, so how to check that? Every element on the right subtree of B, would be greater than B, and every element on the left subtree of B would be lesser than B, right? Now we do insertion in an ABL tree by following the same function of same insert function of binary search tree. After we do the insertion, then we check for balance, right? So one thing that we can be sure about is when I have inserted this new node, I have followed the general principle of insertion into a binary search tree, and I have followed that whether a particular element is lesser, then I would put on the left side. If it is greater, then I would put on the right side of the parent node. Okay, so that thing I know. So the new node has been inserted by following those rules. But only thing is now I have to decide on which part of B, whose side of which subtree of B it has been inserted. So I can just check the value of B with this key value, right? If B is lesser than this key value, let's say I say key B is lesser than key, then I know that since key is greater than B, then it must have been inserted on the right side of B. So that means it's an R rotation. And other way, if B is greater than the key, then I mean the key has been must have been inserted on the left side of B, because key is lesser than B. So that means it's an L rotation. So first L you already got. Now you, by comparing the value of B and the key, you got L or R. So you know LR or LL rotation, and then you simply do the rotations accordingly. Call the rotate function of LL and LR. Okay, so that's how we do that. Okay, again, I'm asking any general doubt in week 5, week 6, any place. These are supposed to be the a bit difficult weeks. Any doubts? Union find data structure, how the union find is working.
Need to
Yes, so
revise
please
this
explain union find.
Union find, okay. Yeah, what are you saying, Mr. Bimlesh?
No, I was saying need to devise union find once more.
Union find, right? See, union find is, wait, just a second.
So please also discuss that complexity part which I asked you on that discourse forum, because you told me to
Complexity of
ask
which one? Complexity of which one?
that union find like the way sir has defined
Okay,
find
okay,
that
okay. Yes, 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 sure.
yeah.
Union find, yeah. Okay, so let us have the first the basic idea of why we are using union find or what it is. So basically how we do Kruskals, let's see that. So we just pick up edges which are already sorted. So I have a sorted, L is a sorted list. L is a sorted list of edges, which we have already got. And then what I would do is I would pick each element from L in the sorted order only. So the minimum weighted edge would be the first element in L, right? So I would pick the minimum weighted edge from L, and then again the next minimum and the next minimum, and I would make the minimum spanning tree. So let's say the first edge is this one. I join these two edges, the minimum value 1. Okay, let's say the second edge is something like this. It may be joined, it may not be joined. So what I mean is, so let's say the first edge is 1, 2, first minimum weighted edge. The second minimum weighted edge is, let's say, 3, 5. The third minimum weighted edge, let's say 4, 6. What does this mean? When I apply Kruskal, and let's say we have many other edges. So when I apply Kruskals, the first edge would be 1, 2, that would be picked up. Right? The second edge would be 3, 5. Right? So I'm not joining. What would Prims would have done? Prims would have started from a particular node, and it would have constructed from that node itself, like this. The tree would never be disconnected. It would go like this as a single structure. Okay, Prims. But Kruskal would not do that. I mean, it may not do that. If the minimum weighted edges are initially such that they are not a part of same component, right, then you are actually essentially forming like this, 3 disconnected edges, and 4, 6, let's say 4, 6 you have. Okay, now let's say you have the, after this again one edge is there, which is, let's say 3, 6. Okay, so then you join. Okay, now you actually made 2 components into a single one. You merged 2 components, I mean 2 separate trees. And likewise, say let's say the next minimum edge is 1, 4. Fine. So you again join this. So finally you get a minimum spanning tree. So basically the idea is Kruskal would grow separate components separately, and in the process of selecting those edges, all those separate components would be merged into one single component, and that single component is your minimum spanning tree at the final stage. But Prince would not grow separate components. It would take one edge and it would just extend next edges from that one single component, right? It would grow like this. So let's say if I take the Kruskal of this same graph, something like this, it would grow like this. It would, let's say, it could take this edge, then it could take this edge, then it would consider this edge, then it would consider this edge. Okay, so Kruskal grows as a single component. Prims grows as a single component. Kruskal grows as separate components, and all those components at the end of the algorithm would be merged together into a single component, and that single component is your MST. Fine. Now, what are the important thing? What is the only important, not R? What is the only important thing that we have to consider in this process is that we do not form cycle. So let's say I also had an edge over here, which is, let's say, before 1, 4, right? I had another minimum edge over here, which is lesser than 1, 4, and let's say which is 6, 5. Okay. So if I take that edge according to Kruskal's approach, I would join 6, 5, but I see that I have formed a cycle now. So we have to somehow keep track of that. I'm not getting into a cycle. So if I get into a cycle, I would simply ignore that edge and I would move to the next edge. So I will not consider 6, 5. I would go for the next available option, which is 1, 4, and I would attach that. This is how Kruskal's basic working happens, right? So what is the important feature that we are doing? What are the 2-3 important steps? First thing is we have to find which vertices. So in the initial stage, when I had only these 3 edges, right? Like this, totally disconnected components. So I have to find to which component each of the edges belong. Sorry, each of the vertices belong. So 1 and 2 over here at this level has to, I mean, they are together into a single component. 3 and 5 are together there into a single component. Accordingly, 4 and 6 are together there into a single component. After that, as soon as I pick the 3 and 6 edge, I am merging the components of 3, 5 and 4, 6 together. So all of them now are together into a single component, right? So I have to keep a track of which vertices are there under a particular component. Okay, so that is one step that we have to do. This is where your union find data structure comes into play. What it does is it simply mixes, I mean, it merges the component. Okay, so find of B, if I write find of B, it simply means it would return the component, of B, vertex. Okay, and what is union? When I write union, if you go to the definition over here, just a second. If I write this union of I comma j, what this would do is it would merge. I mean, it would union. I mean, you are adding, right? It would do union of the two separate components, which are I component and j component. So when we were considering this 3, 6 edge, right? 3, 6 edge. So let's say I give this component as name C2 and this component is C3. Correct? So what I would write union C2, C3. Fine. So that means I would merge this together. And to which it would be merged? I mean, after merging, what should I call? Should I call C2 or should I call C3? That is, we have to have an improvement, and that improvement is we would only merge. So we would merge C2 into C3, or we would merge C3 into C2. That is the question. When I say into, what do I mean? So if you have this thing implemented as a component dictionary, right? You have a component dictionary where you put a vertex I, B, and you get the result. I mean, you store the component in that. So your find function is actually using this component dictionary. I would go into the slide and we would discuss again. So find V is basically you are storing a component data structure, component dictionary, and that component dictionary, the key is the vertices and the value is the component number. Correct. So initially the component number of the vertex would be the vertex itself. So let's say the vertex 3 is component is 3 before the start of the algorithm. But once the algorithm proceeds, whenever I would match two components, right? So whenever I would join this 3,6 edge, right? So what should I do? Should I change the component of all the nodes into C2 to the component of C3? Or should I change the component of all the nodes in C3 to the component of C2? So should I change component of 3 and component of 5 to 3? I mean this component, right? C3, not C3. In dictionary we would actually mark it as, let's say 4 or 6, right? So let's say this component was 6. Name of this component was 6 because any one of the vertex would be picked for naming the component. Okay, that time I was discussing the theory, but now since we are discussing the application, so let's say this component was 6 and let's say this component was named 3 because 3 is one of the vertex over here and 6 is one of the vertex over here. I'm just taking, you can take it to be 5 or 4, anything. But while merging these two components, the decision is whether should I change the component of 3 comma component of 5 to 6, or should I change component of 4 and component of 6 to 3, which is this. So 3 and 6 are the two component names. I am joining the 3 and 6 edge. So when I am doing that join, which vertices I should change the component value of? Should I change 3 and 5 to 6, or should I change 4 and 6 to 3? Right? So that decision is taken by the, I mean, you would take that call by checking the size of each component, right? So very simple idea. Let's say now in both of this component you have only two vertices, correct? But let's say if I have to now merge this component with this whole thing in the next step, I would do that, right? So I know that this component has more number of vertices and this has lesser number of vertices. Okay. Now, since this component has lesser number of vertices, it's easier for me to change the component of these two vertices because I have to traverse through lesser number of vertices to make the change. But if I just change this whole component to the name of this component, right, while merging, then I have to travel through more vertices to make the change. So that decision I would take simply depending upon the size of each component. The component which would have lesser size, I would change the vertices of I would change the component value of all the vertices of that particular component. Okay, that is the simple trick that we are doing while merging. Okay, now let's go over here. So you see find algorithm over here, find returns the component. So that's what I was saying, that component dictionary is maintained and find is simply returning the value of component of I. That's it. Okay, so you know find is returning a value from dictionary, so that is order of 1. Okay, and union I comma j, what are this I and j? These are just the two components that we discussed. So it would just merge the two components. Fine. So how do you merge? By depending upon the size. But you see over here it's written naive implementation. So that technique that we just discussed, that you merge the smaller size component into the larger size component. I mean just renaming thing, right? Merge would anyway happen. Which should you rename? Should you rename 3 to 5 or 3 to 6 or 6 component to 3? The lesser number of vertices are there, I would just rename that because I have to make the changes for lesser number of vertices. That's the simple idea. So, but there is naive implementation, so it's not given over here. If we go to the next slide, improved implementation, right? So here you would see this. If size of C component is lesser than the size of C dash, two components, right? Relabel C as C dash, else relabel C dash as C. Okay. So every time I would do that while doing the union. So if you go to the union function after this, you would see this next implementation. Okay. So what are the things that we need in this process? We need, first we have to keep this size array, right? Otherwise, for each component, I have to maintain a size dictionary which would store the size of that size of that component. And for each vertex, I need to maintain a component dictionary which would store the component of that current vertex. Now, let's say when I merge two separate components, right? While merging, if I see, so why this component is also required is it also helps you in checking for the cyclic thing. So let's say while I was merging this 5 and 6, right, this 6 5 vertex edge was there. Okay, so assume that we are at this stage, that this edge was not there. So this is the stage, and now I am picking 6 5 because it is minimum, right? So when I pick 6 5, so what I would do, basically I would do a union, right? Union of the two components, the union of this component, right? Let's say this component is component number 4. Okay, and union of the 6 5, this separate edge, right? So 6 and 5 are basically the trivial, it is the first time we are joining, right? So let's say the component is named after the edge, which is 6. Now you see, sorry, not 6, 5, because that's the incidence vertex. So I would, when I would do the union, right? When I would do this union, one thing that you would see is what would find return? Find of 4 and find of 5. Both would return 4. Because component of 5 and 4 are same. Why? Because 5 is in the same component as of 4. So when you are actually merging this, sorry, you are adding this edge, which is equivalent to this operation, union of 4 5, that essentially means the find of both of 5 4, these two values, right? For these two values 4 and 5, the find of both of them is returning the same component, means I have already attached all the vertices in the component together, and simply if I add this edge, it would create a loop. So basically this means 6 vertex and 5 vertex corresponding to this edge is already a part of the same component. So I would only do union when they are part of different components. So like this example, let's say this is component 1 and this is component 4, right? So when I take this edge into consideration to join the minimum spanning tree, these two component values are separate, so it would be joined. So when I check that thing over here, you see, when you do union, that equal to factor is appending, not union. See, when you do this union, if component of k is equal to this C old, then you are changing for k in range of n. Okay, so you are checking that factor and then you are merging. If it is not, then you would not merge. Okay, you would move to the next. So the maintaining this component value also helps you to check for cycles. If a cycle is there, then you check for that, else you not. So when if I go to the Kruskal algorithm, you would see the code over there. The not equal to is used. The code is in the next. Okay, so I don't think we have a code for that. Yeah, anyways, fine. So that's, so we use it in the Kruskal algorithm just because of that. I think in the index page we have that code. Just a second. Yeah. See, always add number in component which have greater sizes. So the size is greater than equal to 2, and then we are adding into the component that particular thing. Okay. And if you want to check this factor, you see the component of u must not be equal to the component of v. So whenever I'm considering, if that is so, then I would union the two separate components u and v. Fine. So that simply means you are using this component in order to check for cyclicness that you need while doing the Kruskal algorithm. Okay, so this line is actually checking for your cycles. If component of u is not equal to component of v, if that is the case, then you are sure it's not a cycle, and then you are simply adding the two components together by calling the union method. So union u and union v. So and what is union? Union is simply changing all the component value of u to v, considering the size of u is smaller. So whichever size is smaller, it's changing the vertices of that component. Okay. Now the analysis part of union point, as some of you pointed out, you have to read it. I mean, once you go through it, it would be much clearer. But let me go to the analysis part a little bit. So see, why it is saying that union find is taking actually, I mean, when you are doing union, it's taking log m time. Why its log factor is coming. So the basic intuition behind it is, so let's say I have this many vertices in the graph. Okay, I have these many vertices, and now I am applying Kruskal's algorithm by using union find. Okay, but okay, so that's we would apply that. See, what happens is, at first I would take, let's say this is the minimum value edge. Fine. Let's say the next minimum value edge is this one. Let's say this one. Okay. Let's say that after this, the next minimum value edge is this one. So what is this? I'm calling union, right? When I'm joining this thing, this particular edge with this edge, right? So these are basically two unions I have called. So let me just repeat it. What I mean is, so initially this is the scenario, right? So the component dictionary of each of the vertex for all the vertices would be equal to the vertices itself, the vertex number of that vertex itself. Okay. Then I would do what? I would pick the minimum edge and call union. Let's say this is u, let's say this is v, u vertex and v vertex. So I would call u comma v. Okay. Obviously, before calling u comma v, I would check whether the component of u and v are same or not. So we just discussed the component initial value of component of u and v would be, u's component would be u, v's component would be v itself, right? So obviously these two are different. So we would call component union of u comma v. So this first union call of u comma v means you are just considering the edge. You just picked up the first minimum edge. So one union call happened. First union called u comma v. Let's say after that, the next minimum edge from your sorted list is this one. This edge, right? V comma, let's say t. So again, you would check the component of this particular so once you do this union, right, uv, again remember what we discussed. Once you are doing union, essentially what you would do, you would change the component of one vertex to the other depending upon which component size is more. Now initially the component u had only one vertex, which is u, and component v had only one vertex, which is v itself, right? The trivial case. So both of them size is 1. So it doesn't matter whom you would relabel as which one. So let's say I relabel v as u. Okay. So this is again u. Both of them are u. Fine. Next vertex that I take, next edge that I pick up from the sorted list, Kruskal's second iteration, right? Next smallest vertex, edge. That is, let's say this t edge, u comma t. Now I'm calling it u comma t. Basically, this is this vertex and this vertex joining these two vertices. That edge is the next minimum. Okay. Now, what would be the component of t at this stage? What would be the component of t at this stage? It would be t, right? Trivially, component of t would also be t because this is the first iteration. So, and component of both u comma v, both component of now u comma v, both of them are actually u. Correct. That's why I've renamed it as u. Okay, but this is actually the vertex name is v. I have renamed it to be component u. Fine. So when I merge, before merging, I would check the component of this particular edge with the component of this edge. Now component of t is t and component of uv is u, right? So these two are different and I would call component, union u comma t. Correct. So when I call union u comma t, now see, this is where you have to think about it. Okay. When I have called u comma t, which are my components? So this is my first component. So this is u, component u. And this is the other component over here. I'm adding the edge, right? So this is the t component. So when I call this function union u comma t in the second iteration, u comma t, how many vertices are there in the component u and how many vertices are there in component t, right? When I call this method, the u component has two vertices because in the first iteration I have changed the component of v to u, right? So u and v, both vertices component name is u, this statement, and t is the it has just came into the play, right? It was not initially there. So component of t would be trivially t. So the component number t has only one vertex, which is t itself. Component number u has two vertices, u and v. So we know the size of component u is greater, and that's why what we will do, we will change the component value of that vertex which belongs to a smaller component. So that means I would rename the component of t to be u. I would rename it to u. So that means basically my whole u component grew to be this thing. So now this is my u component. Okay. Now the observation. Observation is, what was the size of t initially? 1. T component size was 1, which is t vertex. What was the size of u component? 2. Correct. When I did the merge, after the merge, right, after one merge, I got a component u whose size is now 3. I just merged it, right? So now u became 3. The observation is that initially the smaller component which I considered, which is t, right, I am at least doubling the size of that smaller component after the merge. That is the observation. Obviously, right, because I am changing the component value of t component only when I have a greater component than that, right? So that means if the first component, the smaller component, in this case the size of t component is 1 because only one vertex t was there. But let's say in the next minimum edge is this one. Okay. And now let's say this component is, let's say this vertex is x and p. And let's say I name this component p component. Fine. Now in the after this step, let's say if I have to join this p component and u component, if I have to join this p component and u component, what is the size of p component? Size of p component would be 2. Size of p component would be 2. Right? Component of p, sorry, not component of p, size of p. Size of p component, size of p component would be 2, and size of u component would be 3. Correct. So let's say after I merge it, obviously it's obvious because I'm merging, I would rename the P component vertices to be U because it has lesser number, just the same logic. So after merging, what would happen? U component size would become 3 plus 2, 5. What is the observation? The observation is the smaller component. Consider the smaller component in both cases. So the smaller component was this one, P, which has size 2. Argument is after making one merge, after making one union, merge means union. After making one union, union means I am just joining these two. Let's say this is the next minimum, so this is union. That is I am merging, right? After which U became 5. So after this union, the size of the component grew to be at least twice. And that's correct, right? Smaller component was 2. It grew to be at least twice. It became 5. It would have been 4, but it became more than that. Okay. So that's the idea. And why it's happening? Because I am only merging when the size I have a greater component. When I have a greater size, right? Then only I'm merging. Otherwise, I would have merged the other way. That was the idea. So I can guarantee that every union operation is actually decreasing the total unmatched vertices, right? At least by decreasing by half or increasing twice, then the size of the minimum component which I am considering in an iteration. It's a bit difficult. Just think, if you understand it, it is very easy. What I am saying is every union operation can guarantee that whenever you are merging, whenever you are doing the union, you are getting a new component after doing the union whose size is at least twice of the smaller component in the union operation. Correct? So if you are doubling up in every iteration, if you are doubling up, you are consuming the the unspanned vertices at a double rate in every iteration of the union. So how many iterations would you need maximum in order to span through all the vertices? It's you are getting the factor of divide by 2, right? Every time you are merging that. So if you are getting a divide by 2 factor, just like in binary search, just like in trees, everywhere, we know when you are dividing the problem space by 2, you get a log n factor, log n base 2 factor. Okay. So that is the intuitive idea. Only thing that I can guarantee is if every union operation at least doubles the size of the smaller component, I can get this double factor, and that's why I can guarantee that after log n number of or log m number of union operation, I would end up spanning through all the vertices. Okay, and that you have to do for m times, so that is basically m log n time. Okay, so that log factor actually comes into play because of the reason that you are merging the smaller component into larger component. If we would have not done that and arbitrarily gone with the process, then I could never guarantee that you would always end up with double the size. Getting the point? So that's why this log n factor comes, and that thing is explained over here, and you apply that log m at most for m elements, you apply that for n log n times. Fine. So that is the complexity part of it. Again, this is a bit tricky analysis, so it's again amortized analysis. How you do that, because the first union is actually taking trivially order of n time only, because you are merging component of equal sizes, right? Then actually when one component grows larger, then you are actually reaping the benefit. So the later operations are better, but the initial operations may be bad, or maybe the initial operations are better, later operations are bad, but average you are getting a log m time, and that's what we call amortized complexity. Fine. So yeah, that was the basic idea. Go through the slides again, watch the lecture, and then maybe revisit this session. I hope it should be clear. That was union find.
Union find basically for two reasons. One is for time complexity and taking care of cycles. Is that the two main?
Correct. Exactly.
Important application of union. Okay.
Yeah. Taking care of cycle was handled by simply maintaining component. Time complexity, that part, that merging the smaller into greater component, only that factor is contributing towards the improvement in time complexity. If you would have simply maintained the component, then also you can check that if component of u not equal to component of v, then you called union of u comma v. That's it. That checks for cycles, right? Okay. So yeah. Fine. So
Can it be so that size of two components are same while at the time of merging?
fine, no problem. You can merge any one of them, but it would be greater than equal to or less than equal to, right? So you can do that. Doesn't matter, right? Only see the thing is, when I argue that you are at least doubling up, how can I argue that in every iteration? I can only argue that when I say that you are merging the smaller into bigger. Then I can say that since it is bigger, it is at least, after I merge, I would at least get twice the size of the small. Correct? Because it
Yes,
is
that is clear.
yeah. When it is equal, it doesn't matter, right? If you are getting at least twice, there you would get exactly twice. There is no
No, then
smaller.
which one to merge? Which one to merge? Which one
Anyone
to
doesn't
take?
matter. Doesn't matter. Anyone you merge, the condition when you do this now, when you apply this greater than size or less than size, you would write greater than equal to size or less than equal to size. You use the equality. If it is equal, no problem. You can merge any one of them. Any one of them, if it is equal. You don't have to worry about that. So when you write the code, you would just write greater than equal to or less than equal to, and that's it. Okay, so this condition, na? Where is that size thing? Yeah. So here you would use greater than equal to in the code. So this is the idea that we discussed over here. That's why it's only written like that. In the code you can write greater than equal to. That's fine. Okay, so that was union. So again, just to summarize, mainly two things we have to track of. The first is I'm not running into a cycle. That can be simply checked by using a component, and the corresponding piece of code is over here. I think where is the index?
Component not equal to component B.
Correct, correct. Yeah, this line. Where did I see it? Yeah, here. Okay. So if that is the case, then you simply call union of u comma v. Fine. And since you are unioning u comma v, obviously you are joining that edge corresponding, joining u and v vertices, right? So that's why you are appending that into your tree, just to keep track of your tree. That's it. TE. Fine. So this is your cyclic check. This is your union operation. Now implicitly this union operations implementation, if I go over here, right? Implementation takes care of this thing. You see the greater than equal to is there. So that we told now that you can use less than equal to or greater than, just use the equality. So that thing is done over here. Greater than equal to. So the union operation implicitly keeps this track. If the size of C new is greater, then I would change the C old vertices to be the component of C new. I mean, sorry, I would change the component of all the vertices in C old to C new. That's what we are doing. You see, I'm changing the component of all X, where X in members of C old, where X is a member of C old component, right? I'm changing the component of all such vertices to C new. Why? Because C new size is more. And since C new size is more, it's better for me to go change the values for all those vertices which are a part of C old. I would have to do that for less number of vertices. That's the idea. Fine. So that is union find. Kruskal, acha, few basic question regarding Dijkstra and Bellman-Ford. Let me ask that. So if there is a negative cycle in a graph, then no algorithm would give you correct result. But in order to detect whether there is a negative cycle in the graph, you have to use either Floyd-Warshall or you can use Bellman-Ford. How to use Bellman-Ford in order to check whether there is a negative weighted cycle in the graph? What do we mean by negative weighted cycle? So negative weighted cycle means the overall sum of all the edges in that cycle is negative. So I have a, let's say I have like this, a cycle is there. Sorry. Right, 6 minus 1, 8. So this is not a negative weighted cycle because the summation of all this whole path is not negative. Fine. So in this kind of cycle, the minimum path would exist. Minimum path exists. It will exist. But if a cycle is there like this, minus 10, 2 and 3. So here the overall sum of this, all the edges in this cycle, that is if I travel across this cycle, right? So my overall sum would be negative. Correct? It would be minus 12. So this is a negative weighted cycle. In such example, your shortest path or minimum path, whatever, shortest path does not exist, because if you are getting a total value of -5 in every round of this cycle, you would end up doing this cycle infinite number of times, and you can say that I am getting a path which is negative infinity, right? So shortest path does not exist. Does not exist. Now your algorithm, what it has to do here, your minimum path or shortest path exists, but Dijkstra cannot give you that path. Dijkstra cannot give you that path. Okay, again another statement can be Dijkstra can never give you that path. That is wrong. Dijkstra may give you, Dijkstra may not give you. Totally depends on how the edges are oriented. Fine. So Dijkstra may give you correct result in this case when the minimum path exists, right? And Dijkstra may not give you correct result. So Dijkstra is not a reliable algorithm in this case.
No, but for Dijkstra, the condition is there should not be any negative edge.
Correct. That's what I'm saying. Dijkstra, the condition is there should not be any negative edge. That's when you can 100% be sure that Dijkstra would give you correct result. But what I am saying, if I tell you that I have given a graph whose one edge is, or let's say some edges are negative, but it's not a negative cycle. There is no question of negative cycle. If cycle comes, then their path is not there. So forget that. But even if I give you a graph which does not have negative cycle, but only negative edges, Dijkstra may give you correct result. May give you. Okay. Not always. Not always. If you want to be 100% sure by applying Dijkstra that the result is correct, you should not have even one negative edge. That is accepted.
Why? Because discussing the correctness of Dijkstra, that minimum separator lemma proof.
Yeah, correct.
That negative thing came from there.
Correct, exactly correct. But what I'm saying is sometimes the questions are twisted. So let's say a question is given like this in the exam, that given a graph with negative edge but not negative cycle, Dijkstra algorithm would never give you correct result, or it would never give you the minimum path. Okay, whether this statement is correct or not. So this statement is not correct. We can have multiple such examples of graph where negative edges are there, and running Dijkstra would give you the minimum path. That can be there. That may be possible. I would show you an example, or I would give some example.
If that negative edge doesn't come in the path of the Dijkstra.
Yeah, simply that. If it is not there in the path, it would give you correct result, right? So yeah, even let's say in the example that we just discussed, that we were not modifying the parent when the initial value was same, right? The question that you said. So in such an example, let's say a graph is such that the destination vertex is connected to a negative edge, but even by using the negative edge, I am getting the total path length to the destination equal to the path length which I got by using another path. Okay, which was equal. So I would not change the parent. It would again give me the correct result, even though there is negative edge. So keep those things in mind. Dijkstra may give you correct result. Dijkstra may not give you correct result when there is negative edge. So Dijkstra should not be used in a graph where even a single negative edge is there. Bellman-Ford would always give you correct result. So Bellman-Ford works for negative edges, or Floyd-Warshall would also give you correct result. So that's fine. But let's say now you have this negative cycle. Not only edge, the overall weight is negative, and that means that basically there is no negative path, there is no minimum path possible, because it would decay down to minus infinity, right? So you need an algorithm to tell you whether given any arbitrary graph, if there is if there is a minimum path possible inside that, also we can say alternatively, if there are no negative weighted cycle, right? So give me that minimum path. But if there is a negative weighted cycle whose overall weight is negative, then you tell me that this graph has a negative weighted cycle and I cannot run any algorithm on it. So basically, an algorithm has to check and tell whether there is a negative weighted cycle or not. If it is not there, tell me the minimum path. If it is there, then I know that there is no minimum path available, and you tell me that since there is a negative weighted cycle, no minimum path is available. This feature you can do with Bellman-Ford algorithm. How you can do that? That also we discussed. I mean, I took an example also, I think. So you have to just run the Bellman-Ford algorithm up to n-1 times. Okay, Bellman-Ford algorithm is nothing but you only check that distance ij condition, right? Distance of I to j, if it is greater than distance of, the vertex that you are doing, that is I to, let's say, the parent, and plus the weight of parent 2j. That simply you apply this condition n-1 times. If it is greater, then you simply modify the distance I to j equal to this part. Okay, so you apply this n-1 times in Bellman-Ford. If you remember, in Bellman-Ford we ran it till n times. Okay, so if I go over here, just a second. Yeah, you see here it is rows. You are running it for rows number of times. I would not run it for rows number of times. What you can do is you simply run it for row minus 1 number of times. Then what does it mean? I think I discussed this in the open session of week 5, that when you run Bellman-Ford for k number of times, so that essentially gives you all path, the minimum path, not all path, the minimum path by using k edges, right? So if I, in a graph G, if I run Bellman-Ford for k times, then the distance dictionary, right? The distance dictionary would store the minimum possible path length to any of the vertices from the source vertex by considering only k edges. So let's say if I consider k plus 1 edge and there is a path which is lesser than the current distance for a particular vertex. So when I use k edges, I take around, let's say, 20 distance to reach a particular vertex. But when I use another edge, k plus 1 edge, right? So let's say we have another edge which is very less, but it is a bit far away from the starting vertex. So by considering k plus 1 edges, we would get 18 as the total length to reach that same vertex. Okay, so k plus 1 edges would not be there. So your distance dictionary would store 20. So easily, if I say it, k times running Bellman-Ford on a graph gives you a path which is of at most k length, and that path is the minimum value considering all the paths of k length. Fine. So now how can we check for this negative weighted cycle by using Bellman-Ford? You run it till n-1 times, and that tells you that all the minimum value of vertices in the distance, right? That is by considering n-1 edges. That is by considering path of minimum length, and those paths are of at most n-1 length. Now we know every tree can be created by using n-1 edges, right? All trees can be created by n-1 edges. Okay, so you store the distance dictionary after running Bellman-Ford for n-1 times in a separate place, right? And after that, you again rerun Bellman-Ford one more time, that is the nth time, on the same graph, right? So what does this nth time iteration of Bellman-Ford means? Now I have all the paths which are considering n edges in the path, right? N edges, n edges long path, right? And the minimum value among all that, right? So n minus 1 time Bellman-Ford gave me n minus 1 edges long path. N times Bellman-Ford gave me n edges long path. We know that any all the sets of vertices can be connected by using n minus 1 edges. So the nth edge, if I get in the nth dictionary, right? I told you that after running Bellman-Ford n minus 1, you keep the dictionary aside in a separate variable. And after running the nth time, if you get any one particular distance that is changed from the n minus 1th dictionary, in the nth dictionary, if it's changed, if it is decreased, then you can be sure that there is a negative weighted cycle. Why? Because if I would have a normal path, right, then that would have been constant in n minus 1 and n as well, both the cases, because doesn't matter I run n plus 2 times, n plus 3 times, n plus infinity number of times, I can only use n minus 1 edge to connect the whole spanning tree, correct? Because it's a tree. So if there are no negative weighted cycle, I may run the Bellman-Ford for 1000 more times, but it would not change the distance dictionary because it has already considered n minus 1 edges. But if there is a negative cycle, then by considering one more extra edge, which is corresponding to the cycle, right? So let's say this is your Bellman-Ford's iteration corresponding to this graph. 0, I take 2, right? Then let's say I take 3 and I stop over here. So I have 3 vertices. So I would run Bellman, I mean, the spanning tree would only consider up to 2 edges, n minus 1 edges, right? So, but if I again run for n edges, right, in order to gain a cycle, so I see that this negative minus 10 is actually reducing the value. Okay, so simply think in terms of code, run Bellman-Ford n minus 1 times, keep the dictionary aside, distance dictionary, run for the nth time, check whether there is a difference between the dictionary that you got after nth iteration of Bellman-Ford and the n minus 1 dictionary which you kept aside. If at least one vertex gives you a difference in value, which is a decrease in value of the distance, then you can say that there is a negative weighted cycle and no minimum path exists. Okay, because it's a negative weighted cycle, so you would decay down to negative infinity. So Bellman-Ford gives you that feature. Okay.
So in a quiz, how a question could be framed around this?
It may be some sentence kind of thing that we discussed. It may be directly just solve. I mean, given a, so you might be asked that adjacency matrix is given, right? Adjacency matrix might be given. Okay, and maybe we can ask that which algorithm can properly find the path, a minimum path, or given this adjacency matrix. I mean, or this graph. So the trick is we have to check whether there is a negative weighted cycle or not. Just draw the graph by doing this adjacency matrix, checking this adjacency matrix, draw the graph. Once you draw the graph, then you see if there is the presence of a negative weighted cycle, you know that Bellman-Ford is the, or Floyd-Warshall, Bellman-Ford or Floyd-Warshall. Both of this can work properly, but obviously Dijkstra would not work. Okay, also we can give an adjacency matrix where there is not a negative weighted cycle, but a negative weighted edge. And the negative weighted edge is placed in such a manner it is not on the path to the minimum path to the source and destination. And we can ask that which algorithm correctly gives result. So all the 3 algorithms would give you result. Bellman-Ford also give you result. Floyd-Warshall and Bellman-Ford would anyway give you correct result. But Dijkstra would also give you correct result because the negative weight is not in the same path. Fine. So if you just mark 2 option correct, then you would get partial marks. Something like that. I mean, just guessing, but yeah.
Okay.
Fine. So that was one more important point. So this is also asked on discourse. You can check that. You have answered over there. So what is the primary difference between Bellman-Ford and Dijkstra? The primary difference is that Dijkstra we always pick the minimum edge, right? We used to pick that minimum, sorry, not minimum edge, minimum distance vertex. The vertex whose distance value is minimum. We pick that and then we check all the edges from that vertex. But in Bellman-Ford we do not do that. It's not required. We simply blindly we reduce, we relax all the edges n times. That's relax means applying this operation. So If you check the CLRS book or many standard book, relax is the term which is corresponding to this operation. Okay, so basically we apply this step n number of times in Bellman-Ford. If you have to check for negative weighted cycle, you apply n number of times only, but separately. Apply n-1 first, then the n. So totality, I am calling that mainly you apply Bellman-Ford algorithm by applying this relaxation operation n number of times without checking for minimum distance vertex between each iteration, right? And that's why you see in Bellman-Ford, I do not have any heap, any min function that is used. We are simply running a 3 nested loop and directly applying this step, right? But in Dijkstra, we pick the minimum distance vertex every time. And initially we did that using simple sort function, right? But later we understood that since we are also dynamically modifying the data set where we are finding the minimum element every time. Modifying means in Dijkstra, what do? We change the value, right? We change the value of each node, the distance value of each node we change as we proceed through the graph, right? And if it is changed, we also change the parent. So basically I'm changing the same data set from where I'm picking the minimum element. I'm dynamically also changing that same data set, right? So whenever this kind of operation happens, that you are picking the minimum or maximum, and within the same process, you are again changing the value itself, right? So in a data set in a sorted data set where you are mainly changing as well as withdrawing, both the things are happening, it's better to use heap, because heap gives you a log n time operation of both the things. But where in an example where we are not changing the data and only extracting the minimum or maximum every time, in that kind of scenario, it's better to use a simple array, sorted array, because you are not changing it. If you would have changed it, then it would have taken order of n time. But since you are not changing it, you can just get the minimum or maximum in order of 1 time. Fine. That's why naive implementation of Kruskal, I mean, without using the union find, even by using union find as well, sorry. So basically the implementation of Kruskal uses simple sorted array. We write edges.sort, right? We did not use heap over there. But Dijkstra, as an advanced implementation, we used heap because we are changing the distance parallelly, picking the minimum distance vertex and changing the distance of other vertices to which the minimum distance vertex is connected. That you are doing. Okay. So heap is used in Dijkstra. So questions can come like this also. In order to improve the efficiency of Dijkstra, which data structures can be used? Let's say number 1 option is sorted array, heap, binary tree, and something like that. Or let's say list. So you answered that. Okay. So in in Dijkstra, in frames, whenever we are changing the data also along with extracting the minimum, we should use heap, because heap's insertion and extraction both are log n time. Okay. But whenever we are not modifying the data but only extracting the data, then it's better to use array, sorted array, because if we would have used insertion, then it would have taken order n time. But since we have not used insertion, I can just get the element in order of 1 time. So like this also theoretical question can come. Okay, so the primary difference between Bellman-Ford and Dijkstra is we do not pick minimum elements. We just go for n times relaxation of all the edges in Bellman-Ford, whereas in Dijkstra we pick up the minimum distance element between each iteration. So those things are done. Trees discussed, heap discussed. Acha, one more important point regarding heap. So in a heap, whenever we are changing a value in a heap, right? So let's say I have a heap like this. Okay, so this is my heap. Let's say I change this value. Okay, whatever it is, I change, and let's say this is a minimum heap. Okay, I change this particular value. Now, when I change this particular value, there can be two possibilities. Again, we have a discourse post on this, and this is very important. So please understand this, and also you can read that post. Change can happen in two ways. So let's say the question asks you that a particular value of heap is updated. Okay, so let's say your update function has been given the index where you should update the heap. But important point is that change or update, whatever you say, that can be two things. Either it can be increased or it can be decreased from its initial value, right? It can be either increased or it can be decreased. Now, obviously, it would also have been provided to you whether the heap is a min heap or a max heap, right? So let's take in this example min heap, okay? And let's consider the first scenario. So when the value is increased, this value is increased. Okay, so if this value is increased, what would happen? We know that the upper elements are, I mean, since it's a min heap, before making the update, upper element must have been smaller than this element, right? Parent element must have been smaller because it's a min heap. But now I am increasing this value more. So obviously, one thing is sure, this element would not go to the top. It would not move above. Okay. But the problem is, since I have increased this value now, initially this element was smaller, right? Initially, this element was smaller than this element. This element was smaller than this element, correct? That's why it's above. But since I have now increased, I don't know whether I have violated the heap property or not. Okay. So the only possibility is this element can move down and this element can move up. But the changed element would never move up because there is a min heap and I have increased the value. Okay. So, but move down can happen. So whenever you check, whenever there is a possibility that your element has to move down, that means you have changed the heap property from to the bottom. I mean, considering you have changed the heap property in your bottom part, right? In the subtree part of your cell. So in your subtree, if you have changed the heap property, there is a chance for that. Which algorithm do you apply? You apply Heapify, right? You apply Heapify algorithm. Okay, so whenever you remember in heap sort, what did we do? We used to take the last element. So if I consider this is a heap, so what did we do in heap sort? We just took this element out, we placed this element over here, okay? And now obviously I know since I have placed the last element at the top position, then I must have, I mean, the worst candidate which is at the bottom, I have placed that at the top. So I have totally destroyed the overall heap order, right? Heap property. So what do we call? We call the Heapify method, so that all the subtree part which is below the node, right, that is actually reinstated with the heap property. So observation is, in a min heap, when I do increasing, I obviously my increased node would never move up, it would move down. That essentially means you have changed the heap property in your subtree part, and that's why you call the Heapify algorithm. Okay. But on the other hand, if you decrease the value, now this is a min heap and you have decreased the value, that means there is a chance that you might be now lesser than your parent. Okay. So in that case, what you have to do? Achha, how much time this would take? Login. We know Heapify takes login time. Fine. But when I have decreased the value, what would happen? I know that I can be now lesser than my parent. Correct. So what you have to do is simply check your parent whether it is lesser or more. No Heapify or nothing. Just check your parent. If it is lesser, I mean, if your current value is lesser than your parent, then you just swap. And how many times you have to do that? You have to do that till you reach the root. Why? Because let's say the root was 10, this value was 15, and your value was 20. But after modification, your value had become 2. In that case, obviously you are lesser. I mean, you should be at the top of the heap, right? So in that case, what we do, we just compare it with your parent, and obviously I see that it's 15, so 15 comes down, this becomes 2, and again you just recursively compare it with the top. So 10 becomes over, 10 comes down, and here we put 2. So this is check parent till root. Okay. So how much time this would take? Worst case, again, you are just traveling to the height, along the height of the heap. So it would be log of n again, which is basically your order of height, that is order of log n. So both cases it would take order of log n time only when you change or update a value of the heap, whether you increase it or decrease it. But both cases would be handled differently. Okay, so when you increase the value in a min heap, heapify would be called. When you decrease the value, you have to check parent till root. So bottom line is, keep this thing in mind. If you understand the algorithm, this is trivial, but it's fine. If you just want to remember it, you remember it in this fashion. Heapify reinstates the heap property in your bottom, at the bottom part, right? So if you are here, your node is here, right? Heapify reinstate the property in the subtree part, this part. Okay, so whenever there is a chance that your node might move down, then you apply Heapify algorithm. So same thing if I tell you in case of a max heap, if this changes to the max heap, then this thing would be reversed. If you increase, right, if you increase the value of a node, then obviously there is a chance that it might move up because it might be more than its parent now. And in max heap, we keep the greater values at the top. So we do this thing when it's increased, and when it is decreased, then we call Heapify. Why? Because if I'm decreasing, let's say I decrease this value in a max heap, correct? Once I decrease this value, I know I initially I was greater than this node. Initially A was greater than B and C. A was greater than B and C. But since now I have decreased the value, I might be lesser than B and C now. So that means A might move down. Correct? So the bottom part is now disturbed. I don't know. So that's why I would apply Heapify. Bottom line is Heapify sorts your bottom part, and if there is a possibility that you move up, then you have to check till the root. Both things are there, and this is very important, and I can tell you 2 questions would be coming from the concept of this part. Okay, at least 2 questions might come from the concept of this part, that what you have to do, how you should apply it. Okay, any doubt in this?
This is clear, sir.
Fine. Okay, so Kruskal, Prim's algorithm, they are same. Dijkstra, Bellman-Ford, Floyd-Warshall, all the things we have discussed. ABL tree a little bit we also discussed. Okay, so if there is any doubt, you can ask. I don't know whether there is something else. Yeah. Any specific doubt, if any one of you have, you can ask, or maybe post in discourse. Otherwise, we would end the session.
I had asked regarding PPA too, but
Okay. Practice programming assignment too. Right, great. So this is which week?
5, sir.
Okay, a taxi driver of an online cab service provider wants to go back to his home after dropping a customer. He wants to reduce the total cost to reach home by picking some customers. Okay, he checks the routes online. So there are some routes available from his current location to his home location where he can earn money by picking some customers. Okay.
We can discuss this tomorrow at the start of the session also.
Yeah, it's normal minimum path algorithm, but is there anything specific that you want to ask about it? Cost between two. Okay, let me just read it then. Cost between two stop represent expenditure. Okay, earning, that's fine. So it may be negative. Yeah, assume no negative weight cycles. So see, that is the thing. Assume there are no negative weight cycle exists in the graph. So obviously there is a negative. The proper path is there. So, but since this is negative, cost can be there, right? Cost can be negative. That is basically the edge weight can be negative. So you have to use Bellman-Ford or Floyd Warshall, depending upon whichever you are comfortable in. They are also given two integers, source represents the current location of the taxi driver, destination represents the home location of the taxi driver. The function should return the minimum cost route in the format for source to destination. Fine. So what is the problem? I mean, generally any specific problem? I would discuss it then tomorrow. If you want the proper implementation.
Not concept wise. I mean, how to approach this.
So this is just Bellman-Ford algorithm, right? You have to find the minimum path. There is, I mean, so this dictionary is given in a different manner. The cost is destination index and start indexes are given. This cost is basically your edge weight. Source index is the vertex. So source index is basically your first vertex. Destination index is the second vertex. So this is U, source index is U, destination index is V, and cost is basically the edge weight of UV. So route map is basically your graph. Your graph is ready, right? On this graph, you have to apply Bellman-Ford. Whatever result you get, that's your answer. So if I see this, if you have any doubt in the implementation part of this, I'm saying just it's Bellman-Ford, but if you have any doubt in the implementation, then we can discuss it. I mean, in a live coding kind of session, or maybe in the next session, or maybe I can post the explanation of the code on Discourse. Okay.
Okay, sir.
Yeah. So observation is this part, that this is there now, that given two integer source represent current location. Where is that negative thing? Okay. So it was written now that it can be negative. Earning, so it may be negative. Yeah, this part. Yeah. Fine. Okay. So maybe I would give the description.
Small doubt, sir.
Fine.
This graded 7 can we discuss? One question.
Yeah, please.
Graded 7.
Which one?
Question number 9. Graded assignment.
Which week?
7. Week 7.
Week 7 graded assignment.
Yeah.
Just a second. Week 7.
It's completed.
It's completed, no?
Yeah. Question 9.
Just a second. Anyways, week 7 would be again discussed tomorrow, but still we are checking. Just a second. Graded assignment 7. This question?
Yeah. In that, in feedback, it has been given as 2250 with some lengths. Length of C3, I am unable to understand how it is. And D2. These two, I think there is a small instruction. C should be 2 and D should be 3. Is my view.
C there should be 2, you are saying, right? And
yeah,
D should
and
be
D
3.
should be 3. Yeah.
Okay, and these two values are separate, so obviously it would change the total. So
and
what is your total coming?
2270.
2270. Fine.
But first of all, how to take that from the above tree only? No, there is a tree given above.
Yeah. Correct,
number 8.
So exactly. Let me just okay. So let's solve this. Just a second. From the tree only.
Yeah. The tree was, I think, in question number 7, not in this question also. Question number 8, previous question.
No problem. We have this thing now. Okay. So which tree are you saying? We have to draw the tree. This character is given na, A, B, C, D, E. This frequency is there. You have to
Okay.
draw the tree on the basis of this frequency.
Oh, then that means I don't know how to, because I consider the tree above. Just
No. So you have to draw the tree. See, the idea of Huffman coding is, so I would first recommend you to watch the lecture of this Huffman coding, then it would be much clearer. But still, I'm just mentioning this.
So based on this probability, we can make that length.
Correct. Based on the probability. That's discussed in the lecture. So basically, I'm not solving it. I'm telling you just the overall thing. I would have solved it if there was a genuine problem, but see how this is done is, let's say, no issues. So let's say A, B, C, D, E are the 5 characters. Huh? Let's say this is 10, this is 20, whatever value. There it was in point. I am just taking some like this, some any value, right? 30, 40, 50. Okay. Now there it was given in terms of probability. I am just considering 10, 20, 30 because I can say that this 10, 20 are the exact frequency.
Okay.
Fine. I'm just considering that. Anyways, it can be coming in any way in the exam. Okay. So okay. So how do you do that? What is the main idea? Huffman coding is basically a greedy idea. What is the greedy idea? That the characters which are occurring maximum number of times, I need to represent them with least number of bits. That would ensure that I have total length of the file would be lesser. Okay, total length of the string, would be lesser. So characters which are occurring maximum number of times in the text, right, in the string or text, whatever, you represent that with the least number of bits. Okay. So that's the idea. Now how to do that? So since you have already seen the tree kind of thing, so let's say I create a tree like this. Okay. Suppose this is the Huffman tree, suppose. Fine. And I am telling you that, let's say this node or this node, any one of these two nodes, you have to represent for E. So I would represent E with this node, or I would represent E with this node. What do I mean by I would represent? So let's say this is 0. All the left side would be 0 or 1. I mean, we draw the Huffman tree like that, right? So we just all the left side I'm putting 0, right side I'm putting 1, right side is 1, left side is 0. Fine. So here E would be represented using 0 if I keep E over here. If I keep E over here, E would be represented using 0, 0, 1, 0. Now, if I keep E at the bottom, then E is taking so many more bits. And since E is occurring maximum number of times, it would be a bad design. Okay. So the idea is I would keep E towards the top. How to do that? I can keep E towards the top, and I would keep at bottom, I would keep those elements which are occurring least number of times at the bottom. Right? Now that's the simple idea. And how do you draw the tree corresponding to that? Pick the minimum elements and draw the tree. I'm just giving the demo. Pick the minimum element 10, right? A, right? You pick A, correct? And like this we join. And then the minimum element is B. So pick B. Like this you join. What is the summation? 20 plus 10, which is 30. So store 30 over here. So this is 10, this is 20. Now, once you have merged, once you have joined these two, so just replace this thing in your mind, replace this thing with a value 30, the summation 10 plus 20, 30, right? So 30. This 30 I have replaced with this. Now this is the condition of your data set. Now again, repeat the same step, pick the two minimum values. Okay.
30 and 40.
30 and 40. Not 40. One important thing is I said this is your whole, this is the whole data set.
It means 30, 30.
30, 30, correct. So 30, 30 I have to pick. So I again pick the C over here. Okay, and I merge these two. This was 30, so 60.
Okay.
Fine. Again merge the whole thing. Since you have merged C now, so this is 60, right? So now it would be 60. Now pick the minimum. Now that minimum is 40 and 50, correct? Yeah. 60 is more. So you pick 40 and 50 separately. So I would pick 40. You can place it anywhere, doesn't matter. I'm just writing in this place. So pick D, which is 40. Pick E, which is 50. Separately, I'm not joining it with this tree. And 50 plus 40 is 90. keep it as a separate tree. See, here it is
Okay.
component 2, component 1. Why? Because these two are separate, right? It's not part of this tree. 60 was, if the minimum would have been 60 and something else, like previously we picked 30 for C and this one, then I would grow it on the same tree. But here D and E are separate. So I'm just doing it separate. Now I have merged D and E, so now it would be 90. 2 elements. Obviously, only 2 are there. So now I would just merge these two. Now I would join the 2 components and it's 150. A Huffman tree is created. Just put all left 0, all right 1, right 1, right 1, 0, 0, 1. Now you see,
So D comes 0.
implicitly,
D2.
correct, correct. Implicitly E is at the top, and A and B, which were occurring least number, least number of times, they are at the bottom. That's the idea.
Okay.
One important again question is, just since we are on this topic, whatever we did, what are we doing on this data set? We are extracting the minimum and simultaneously we are again changing the data set, correct? I changed the 30 to 60. Which data structure would be beneficial? Heap.
Heap.
Because we are modifying as well as extracting the minimum simultaneously.
Okay.
Yeah, so that's the idea.
So we have to create this and find the length.
Sure.
That's what I okay, thank you.
Okay,
Excuse me, sir.
correct. Yeah.
Sir, how exactly did we infer that E is at the top? Like I got for B and C. How did we infer for E?
How did we infer for B? We just picked up, right? 40, 50 we picked up and placed it. This is just an example. Okay, so this was just the example tree. This is not the correct tree. Correct tree is this one.
That values were there, no 0.22.
Yeah.
Probabilities were there. Based on the probability, maybe we
based on the probability, you have to just like that. I use 10, 20. You just use those factors.
Yeah, got it.
Right, got it, sir.
Sure. Okay, so this tree is just on the data that I took. Huh? I mean, you have to draw your tree on. Yeah, correct.
Yes, yes. Okay.
Sure, sure. Okay.
Thank you.
Thanks. Thank you all then. All the best for the exam. Anyway, we would have one more session tomorrow. Yeah.
Thank you, sir. Good night.
Thanks. Good night.